Hello everyone, welcome to class. Today we will talk about the advanced Keras API. We will learn how to use the advanced features in Keras, such as creating a neural network with branches or develop your own matrix. First of all, we want to use Keras API to go beyond the sequential model. So far, we are building the sequential model, which means we don't have branches in our neural networks. Here are two examples of a model with branches. The first is the multi-input model. Suppose we want to predict the price of a product, for example, clothes or house. Then we can use multi-model data. Suppose we are predicting the price of a house. We can use the metadata or meta information, such as the location of the house, the age, the number of rooms. Remember the Boston house prediction example, house price prediction. So we can use a dense module to process the meta information. Second, we may have the text description written by the agent, real estate agent. Then we can use the other module to handle the text information, right? To encode the text into vectors. And we may have the pictures of the house, right? So we can use a convolution neural network to process the image. And then we can use the Keras API to merge the output of the three modules together, and then use the merge the layer to predict the price of the house. This is an example of multi-input model. The second example is the multi-output model. We can use a single feature to predict different information. For example, we can use the novel's text, the content of the novel, and use the LSTM or other text processing module to convert the input as vectors, and then use the vector to classify the genre. We can use the same output to predict the genre, right? It's a classification problem of which genre the novel belongs to, and predict the publish date. So we can also use Keras API to build a multi-output model. Moreover, most modern convolutional neural networks have branches. Here is an example of Inception Module. The Inception Module was proposed by Google and was the winner of ImageNet competition in 2014. Here's an example of the module in the neural network. Each module has 4 branches. For the input, it will be sent into 4 different branches. And each branch has different size of filters and different strides. As we can see, the first branch have a 1-by-1 convolution neural network with strides 2. You may wonder why we need a 1-by-1 convolution neural network, because we can just change the weight of the input. This is because the input data of an image is a 3-dimensional tensor, right? So the 1-by-1 filter is focused on filter the channel size. It's a channel-wise filter. In the first layer, the size of the channel is 3 because we have RGB channel for a colorful image, and the channel size increase with the number of layers. Note that the width and the length of the input tensor of an input image decrease with the number of layers. decrease with the increase of the layers because we are using the max pooling, right? However, the size of the channel increase with the deeper of the layers, increase with the depth of the neural networks. So it's better to have a channel-wise filter first to reduce the number of parameters in the channel direction, channel axis. This is why we have a one-by-one filter. Okay, so as shown here, the second branch also have a one-by-one filter first, and then have a 3x3 filter with stride 2. Okay, the default stride is 1. Okay, the third branch has the 3x3 filter and use the average pooling first, and then apply the 3x3 filter. The fourth branch is 1x1 followed by 3x3 filter and then a 3x3 filter with stride of 2. So the Inception module tries to apply different size and stride of filters to the same input inside one module, and then they concatenate or combine all the output features together and then send to the next Inception module. Another important feature of modern convolutional neural network is the residual connection. It was proposed by Kai-Ming He in 2015. The ResNet was also the winner of ImageNet competition. Okay, the residual connection has a skip connection to the following layers. The residual connection wants to solve the managed gradient problem. The managed gradient problem is that the information of the gradient becomes smaller and smaller after passing through multiple layers. So if your neural network is too deep, you will lose the gradient information. The skip connection forces the neural network to learn better results than previous layers. So if the results doesn't improve after going through multiple layers, we can just use the output of previous layers. So this skip connection forces the network model to learn better results after going through more layers, after become deeper. Now let's look at an example of Keras functional API. First, we import the input at the layers from Keras. Note the main difference is that we don't call the sequential function anymore. So the input, let's create input tensor and define the input shape. So it's called input tensor. Then we use the layer as a function. Now a layer is a function. So we create a dense function by calling the layers.dense, right? And we define the output dimension and the activation function. So here's the key. We use the output dense as a function, then we pass the input tensor, and then output the tensor function. So we pass the input tensor we create, and then have a new tensor called output tensor. So a layer may be called on a tensor and it returns a tensor. This is the basic of Keras functional API. Here is an example to use functional API to create a sequential model. So we first create the input tensor with dimension 64, and then we add two dense layers. But now we use the dense layer as function, so we just use the layers.dense and define the output dimension and activation function. Remember, this is a function, so we pass the input tensor inside. More specific, it's a function pointer, so we use it as a function. And then the output tensor, we can use the same. We can pass the output tensor to the next layer function, right, as the input. Also, we can use the same name for the second output tensor, because if you don't want to save the intermediate result, you can use the same name for all the output vectors. And then we pass the output to next layer. Again, the next layer is the output layer. The activation function is the softmax. Okay, so we can use this model to classify data with 10 class. Okay, finally, this is our final result, so we name it as output tensor. Okay, to compile the model, we call the Keras model, and then first pass the input tensor, then output tensor, and the model is done, or is ready to be compiled. Let's compare with our original sequential model. So before this class, we are using the sequential function, right? So we call the sequential function to create a sequential model, and we call the add function to add the layers to the model. So that's the difference. Now we don't use the sequential model, right? And we use there as a function and pass the tensor to each layer. Let's use functional API to build a question answering model. A question answering model has two inputs. First, a natural language question, and then a reference text, such as news article. So for both input, they are text input. We can use the embedding to embed the text into a dense vector, and then use LSTM to process to encode the input. So both branch have the same architecture, but with different parameters. The output is one word answer. Suppose we can use the answer is very short and only have one word. So it's a classification problem. Multi-class classification. We use the softmax over some predefined vocabulary. So our question answering model has two input branch, and then we concatenate the two feature vectors together, and then use some dense layer to do multi-class classification. Here is the code of the question answering model. We first define the vocabulary size of the reference text and the question. We choose 10,000 words for the reference text and the question. For the answer, we use 500 vocabulary or 500 words for the answer. So first, let's write the code of the reference text. First, we create an input tensor for the reference text input. We need to define the shape, but we can use none as the input. So this means we can accept input with different vocabulary size. And also we add a reference name of our tensor, so we can easily identify what the tensor is. Then we pass the text input tensor to the embedding layer. Here, by using the Keras API, we use the embedding layer as function. So we define the output dimension, which is 64. Right, so we will reduce dimension of input from 10,000 to 64. So the input size is the text vocabulary size, right? And then the output is 64. And the embedding layer will generate a new tensor embedded text. Then again, we use embedded text as the input of the LSTM layer, and then the LSTM layer output the encoded text. we repeat the 3 steps for the question input. Define the input tensor. Then we define the embedding layer. Because the embedding layer define the input size and output size, so our tensor can use none as the shape, right? So the question input will, after processed by the embedding layer, will generate the embedding question, and the embedding question after processed by LSTM layer will generate the encoded question. Finally, we concatenate. Look at this picture. We concatenate those two outputs vector. So we just call the layers concatenate function, and it will concatenate the two input. We pass an array of inputs into the function, and it will generate an concatenate tensor. Finally, we pass the concatenate tensor to the final dense layer, which use softmax as activation function, and the output is the number of answers. So we take the question answering problem as a classification problem. Finally, we pass the input and output to the model and create a model. Because we have multiple inputs, we pass an array of inputs to the model. Then we compile the model. So that's it. That's how to create a multi-input model. Let's train our model. Because we have 2 inputs, so we need 2 input data. Here we create 3 data, or text, question, and answers using random number generator in NumPy. So we randomly generate numbers, and we just pass the text and the question array. So we need to pass an input data array to the feed function. Then it will use the input as the data, or the training data for our input. The output, the labels is the answer. Okay, so this almost the same as sequential model. Almost the same. Just pass the array for multiple input. But we have another option. We can pass a dictionary. For dictionary is a key value pair, so we can use the name of our tensor as a key. This makes the code more friendly, easier to understand. Choose the option you like. Now let's look at the multi-output model. Suppose we have social media post data, and we want to predict the profile of the author of the post. For example, we want to predict the age, or the income level, or the gender of the author of the post. So we can use, for example, 1D convolution to process the text in the post, and then use the feature, use the extract feature to predict different information like the age, income, or gender. All information are used the dense layer, but we can also use different type of layers. So we can share the same feature base model and then retrain to predict different question. Right? Here is the implementation of the multi-output model. First, we choose the vocabulary size, which is 50,000, and then we define the number of income groups. We classify the income into 10 groups. So first, we create an input tensor for the post input. And then the post input will pass through the embedding layer. So the embedding layer will reduce dimension to 256. So the new output embedded post is a vector with 256 entries. Okay, now we have the embedded post. the feature vector of the pose, we can use the convolution neural network, 1D convolution, to process the embedded pose. And we use the same pointer name, same reference name for different output tensor. If you are not going to use all output layers, you can use the same variable name. Okay, so we use X. So the final X is the feature extract of the social media post. Then we pass to different dense layer. First, we pass the X vector to the edge prediction, because edge prediction is a regression problem, so we don't have activation function. And the second is the income prediction, which is a multi-class classification problem. We have 10 class, so we create a softmax function, and then we give a name to the tensor, which is income. And then the final, the gender, is binary classification. Here we only define 2 gender. So the input, the activation function is sigmoid function. Okay, so we can use the same convolution neural network to extract features and use them for different problems. Finally, we create the model by passing the post tensor, the input tensor, and the 3 output tensors, the age prediction, the income prediction, and the gender prediction. Because we have different types of tensors, we need to use different loss functions. So in the compile function, we pass an array of loss functions, the name of loss functions. For the age, we use the MSE mean square error. For the income, we use categorical cross entropy for the softmax. And for gender, we use binary cross entropy. Again, we can use different approach and pass a dictionary to the compile function. Age, MSE, income, right? Cross entropy is more readable. In addition, we can assign weight to different loss functions. Depends on which prediction is more important for you. Suppose we think the gender classification is the most important in our application. We can assign high weight to the binary cross entropy, right? We give it 10. And the second important one is the income classification. So we give weight 1 to the income classification. And the age prediction is less important, so we give just 0.25. We can use the Keras API to create any type of neural networks as we like, but there is one constraint. We cannot create a neural network with cycles, so we need to create a directed acyclic graph of neural networks. Here is another example of multi-input module. This is the Inception module. We have seen it before. So there are 4 branches of input. The first is an 1x1 filter, the convolution 2D with 1x1 filter with stride 2. And the second is also a 1x1 convolution filter, then a 3x3 with stride 2. The third branch goes through an average pooling with 3x3 filters and a stride 2. Then go to the 3x3 convolution 2D. Okay. So the fourth one goes through the 1x1 filter, and then the 3x3 convolution 2D filter, and then the 3x3 2D filter with stride 2. Okay, so there are 4 branches in the Inception module. So what is the purpose of 1x1 convolution filter? Why we need to handle only 1 pixel? The reason is that, in fact, we are not handle only 1 pixel. we are trying to reduce the channel dimension. This is because in convolution filter, we only list the size of the width and height, but we neglect the channel dimension. We didn't show the channel dimension. However, remember that a colorful image is a 3D tensor, which include the width and height and the 3 channels for color, the RGB channel. Moreover, the channel size, the channel dimension increase when we go deeper in a convolutional neural network, right? Remember that the size of the image or the width and height of image usually reduce when we go deeper because we have the max pooling. But the channel size, the number of filters increase when we go deeper in the neural network. So it's a good practice to reduce the channel size first, then do the convolution, apply the 2D convolution. So in the first version of Inception module, the naive version, it doesn't include the 1-by-1 convolution. And then the researcher finds it's more efficient and can significantly reduce the number of parameters by applying a 1-by-1 filter to reduce the channel size first, or then apply the 2D filter to the input tensor. So that's why the Inception module now all include the 1-by-1 convolution in its 4 branches. Let's implement the Inception module using Keras API. Okay, so there are 4 branches. For first branch A, it's a 1-by-1 filter, and all the output dimension is 120A for all 4 branches. Okay, so for the first input, we set the stride to 2 and the filter size to 1. The activation is Redu. And for the second branch, the first layer is the 1-by-1 2D filter, and the second is the 3-by-3 filter with stride 2. And for the branch C, there is the average pooling 2D, and then the 3-by-3 2D convolution filter. And for French D, there are 3 layers, 1-by-1 followed by 3-by-3, and then followed by 3-by-3 2D filter with stride 2. Finally, we concatenate the output of the 4 branches and make it the output of the Inception module. The residual connection may be the most important feature of modern deep learning networks. So actually using Keras API is very easy to implement the residual connection. So first we have an input tensor X, and X can go through multiple convolution layer or other neural network layers. And finally, you just add the X with the final output of the layer, right? So the X is this skip connection. So we just add the X with the output of the layers. The output goes through multiple layers, add them together, then we can create a residual connection. The residual connection can solve the managed gradient problem. The managed gradient problem is that a signal becomes smaller after propagated through multi-layers and may be lost eventually, managed. It's a serious problem, especially for a very deep network. So actually in the LSTM, there's a similar feature. It's called the carry track. The LSTM uses a carry track to propagate the signal parallel to the main track, right? And it has a forget gate to remove the unnecessary information. Okay, but in residual network, it's just a simple jump connection. It is simple but very effective. So now almost every modern neural network include the residual connection. We can combine the Keras functional API with pre-trained model and share the layers and the models for different output range. Here is an example of a dual camera image classification example. We use the pre-trained model of Xception, which was proposed by Keras author Shole, and we will have two input from two cameras, the left input and the right input. Okay, the both input are passed into the same pre-trained model, and then generate two output. So there is left features, the left input, left features, right input, right features. And finally, we concatenate the features together and make a merged features output. Besides Keras functional API, we can inherit the model class and override the Keras model to create our own custom model. Here is an example. Suppose we want to train a model to rank the customer support tickets by priority. So the input, there are three inputs, the title and the text body and the text of the customer request. And we will concatenate the input, three inputs together, and then go through a dance layer. Then finally predict the priority and the department that can process the customer ticket. Okay, so to override a Keras model, we first need to define our layers in the initiate. So we create the concatenate layer and the mixing layer here, and the priority scalar, which is a sigmoid function, and then the department classifier, the multi-class classification using softmax as an activation function. And then when new the model, Keras will call this function. So we need to override the call method. That's the most important. The input will be passed to the call method. So we will receive three inputs: the title, text body, and the text in an array, because the user can pass an array of three input. So we got the three tensors, then we use the concatenate layer, which we initialize in the initiate of the model, right? And then just use it like the functional API. We pass the features through a dense layer, the mixing layer, and then we pass the features to the priority layer and the department classifiers. And finally, we return the results, the output tensor. So we can inherit the Keras model and then override the initiate and the call to create our own model. Let's test our model. So we can pass the number of departments when we create a model, and then we pass the input in dictionary form to the model, right? Other things are the same. We compile the model and pass different those functions and also the matrix, and then we train the model using the fit function. We call it fit method to train the model, and then we evaluate. We pass the three data and the two labels to the fit function, and we evaluate on the test data. And finally, we can use predict to output the final prediction of priority and the department. Now let's look at another important feature: monitoring model training. During the training, we can do something to help improve the accuracy or save the model. So first, we can save the model at predefined checkpoint. Many times we need to save in the current rate of the model during training, especially when you are using the free online resource like Kaggle or Colab. It may automatically interrupt you after a period of time. So it's better for you to save the checkpoint. It's a good practice to save models periodically. Also, we can do early stopping. When we observe there's a possibility of overfitting, which means there may be a crossover of the validation accuracy and the training accuracy, we can do early stopping. Additionally, we can do the dynamically adjusting parameters. We can use an adaptive learning rate. Usually in the beginning of the training, we will have a larger learning rate to quickly find a possible low error rate, right? But however, when the error rate didn't improve, when we hit a plateau that didn't improve a lot, or even it not improve at all, we can use a smaller learning rate to fine-tune our result to improve a little bit. So we can adjust the parameters dynamically. Finally, we can visualize the model. It's very helpful to debug the connection, the architecture of the model, right, by visualizing the graph of our neural networks. Keras provide a callback function to let us do our own task during training. The first callback function is the early stopping function. We can interrupt the training when the accuracy has stopped improving for several epochs, for at least more than one epoch. And also we can save our model at the model checkpoint callback function. We can, for example, save the current weight after every epoch. So first we import the callback function from the Keras, and then we create a callback list, which is an array. We will pass the list to the feed function. Okay, so we use first the callback's early stopping callback function, and we define that we want to monitor the accuracy, and we set the patience to 1, which means we will stop training if the accuracy does not improve after one epoch. Also, we pass the second callback is the model checkpoint. We define the name and the file path of the model, and the monitor parameter is the validation loss. And we can set the option that set best only. So whenever we have a lower validation loss, we will save the current model checkpoint. Okay, so once we have the callback list, we can just pass it to the feed function. So then during training, Keras will automatically call the callback function defined in our callback list. Now let's see how to adjust the learning rate dynamically. The callback function is called ReduceLR, which means learning rate on parental. Also, ReduceLR on parental callback function can help us to adjust the learning rate. Okay, so it uses a factor to adjust the learning rate. So the learning rate will be multiplied by the factor after predefined epochs. And here again, the parameter patience, which means the epochs before callback is triggered. So we add the ReduceLR on parental. We monitor the validation loss and set the factor 0.1 and the patience to 10, which means we will divide the vector. We will multiply the vector by 0.1 after 10 epochs if the validation loss does not improve. We can implement our own callback function by inheriting the Keras callback class. The callback class provides the following methods that we can override. It represents the timing during the processing, during the training. So we can implement a callback on epoch begin or epoch end, or on bench begin or bench end, or even the beginning of the training or the end of the training. Let's try to implement our own callback class, which is called activation logger. The goal of the activation logger is to save the output of the activation functions. Right. So first we need to define the set model to override the set model function, and then we first save the model, and then we connect all the output. We make a list of the outputs of each layers in our model. So for layers in models layer, we make a list of the layer output. It's called layer outputs. Then we create a new Keras model by pass the input and the layer outputs. Also, after each epoch, or at the end of each epoch, we will try to first we check if we have validation data. So because we will use the validation data to calculate the activation. Then if we have, we will get the first sample of the validation data and then make a prediction. So the prediction will do the inference and will calculate. It will be activate the necessary activation functions. And then we open a file called activation at epoch and use the epoch number as the end of the file name and save it in MPZ format. And then we just save the outputs. So we use predict to calculate the activations of each layer, and then just save the activations to an MPZ file. This is the activation logger. We can then visualize the activations later. Keras also support the TensorBoard callback. TensorBoard is a very powerful tool for training. It can help us to visualize the accuracy and loss, or even the activations of each layer, or the structure. It will draw the graph of our neural network, so we can visualize the architecture of our model. So TensorBoard is very useful. The Keras support the necessary information. It will provide the necessary information to TensorBoard. So it's provide a TensorBoard callback function. To use TensorBoard, first we need to assign the log directory where we save the information, the metadata. And then we can also define the frequency, histogram frequency, and the embedding size frequency. Then during training, we just pass the TensorBoard callback like other callback functions, pass the list to callbacks. Once the training is done, we can visualize the data or the results using the TensorBoard provided by TensorFlow. It's a standalone program, so you can use it in command line. Just type the TensorBoard and give it the log directory of your meta information, and then assign a host. Then you can visualize the data. You can use the TensorBoard through your web browser. Let's train a model with TensorBoard. Let's use the IMDb example, which is a binary classification, to classify a review as negative or positive, right? So we load the IMDb data and paste in the input sequence, and then we build a simple model using sequential function. Then use embedding, convolution 1D, max pooling 1D, convolution 1D, and the global max pooling 1D. Finally, this output is a dense output, one-dimensional output of a dense layer. Then we compile it as use a binary cross entropy, and then we create a TensorBoard callback function and pass to the callbacks list, right? So doing training, when we call the fit function, we pass the callback list. After training, we run the TensorBoard program and see the training results through our browser. Here's the TensorBoard user interface. It's use the web interface. So first, it shows the accuracy and the loss of training. Under the histogram tab, we can see the activation histogram of each layer. So here's the activation of the convolution 1D output, and one second layer of convolution 1D, convolution 1D2, and the dense layer. The tensor board can also be used to visualize the word-embedding results. The word-embedding induces the dimensionality reduction. It can reduce the dimension of high-dimension vectors, a sparse high-dimension vector, to dense, smaller vectors, and keep the relationship of those data. So it's good to visualize the embedding we learned. We will talk more about word embedding visualization when we formally introduce word embedding. TensorBoard can also be used to visualize the network graph of your model. It's very helpful for debugging because it's very hard to debug the source code if your network is very large and complicated. However, by visualizing the graph, you can easily see the connection error. It's much easier for human to debug on graph or to see the connection error, the wrong connections. Because sometimes you can also generate the output with wrong connections. So it's helpful to visualize your network. You can also call the plot model function of Keras to visualize your model. The plot model function will save an image to your disk. Here's an example. The PNG image is saved by the Keras plot model, but the input will be on top of the total model. So at the top of the image is the input, or the output is at the bottom. Now I want to introduce some techniques that can improve model accuracy. The first one is the bench normalization. Bench normalization was proposed by Sir Girofi and Christian Zagadi. Bench normalization, accelerating deep network training by reducing internal covariant shift, published in ICML 2015. So the basic idea is to normalize data after every transformation. And the author showed that it can enhance backpropagation. And also some deep networks can only be trained with bench normalization. So this technique is very helpful. To use it is simply just add the bench normalization after each layer. So after each output, you can do a normalization of the data, which is what this sentence means. Normalize data after every transformation, after every layer and the bench normalization layer. The authors of bench normalization has also published more paper, which is called bench renormalization, to show more evidence that normalization can help improve the model. Another important technique is the Depthwise separable convolution, which can reduce the number of parameters in the convolutional neural network. The idea is to separate the channel. So we will do the spatial filtering on each channel independently, and then we will combine the output using a channel-wise filter. Using this approach, we can have much less parameters, and even with slightly better accuracy. It was proposed by the Keras author, the author of our textbook, Francois Cholet. Cholet published a paper on in CBPR, which is called Xception, Deep Learning with Depthwise Separable Convolutions. The idea comes from Inception, the one-by-one filter. So Shirley called his method Xception, the extreme Inception. The separable convolution assume that the cross-channel correlations and the spatial correlations can be handled, can be mapped completely separately. So the separable convolution consists of two steps. The first is the depthwise convolution, and the second is pointwise convolution. So first, separable, the depthwise convolution handle each channel separately. So it applies the 2D convolution filter to each channel, the kernel to each channel independently, and then output, for example, 3 feature map. And then the second step, pointwise, use the channel-wise filter to combine the 3 independent feature map and generate the output feature map. Depends on your output dimension. Okay, so it first use 2-dimension filter to process each channel independently, and then use the pointwise convolution to combine the output feature map and make the output. How the separable convolution reduce the number of parameters? Let's first review the normal convolution. Suppose we have one kernel of a 5 by 5 by 3 kernel, and we want to apply it to a 12 by 12 by 3 input tensor, right? And this kernel will generate the 8 by 8 by 1 output. This is the normal convolution of one kernel without padding. However, if we want to have a 256 dimension output, we will need 256 kernels. So the total number of parameters in this convolution layer, will be 256 times 5 times 5 times 3 plus 1 BIOS, which is equal to 19,456 parameters. So one convolution neural network will have around 20,000 parameters. On the other hand, the separable convolution divide the process into two steps. Let's look at the first step, depthwise. We will have 3 5 by 5 by 1 kernel. So the number of parameters 5 times 5 times 1 times 3 is actually equal to the normal kernel, normal convolution. The difference is in the second step, the pointwise. For pointwise, we will need a 1 by 1 point wise 3, 1 by 1 by 3 filter. So the total number of parameters is 1 by 1 by 3 plus 1 BIOS multiplied by 256. As you can see, this is much less than the original 5 times 5 times 3 times 256. Let's compare the normal convolution and the depthwise separable convolution side by side. A normal convolution, suppose we have a 5 by 5 by 3 kernel. The size of the parameters of this layer is 5 times 5 times 3 plus 1 multiplied by 256. The total number of parameters is 19,456. On the other hand, the depthwise plus pointwise filter size is the 5 times 5 times 1 times 3 plus the 1 by 1 times 1 times 3 plus 1 BIOS is just 4 of the pointwise filter. The size of the pointwise filter is just 4 entries multiplied by 256. So the total number of parameters is just 1099. Is an order of magnitude less than the original normal convolution. So depthwise separable is actually very common in embedded model. Let's test separable convolution in Colab. To use separable convolution, just replace conv2D with separable convolution 2D. So we create a sequential model and add one separable convolution 2D layer, right? And we can use summary to see the results. For input shape 12 by 12 by 3 and 5 by 5 filters with output dimension 256. Right, the parameters is indeed 1099. We use bias. We set the use bias true. You can choose to not use bias. For the normal convolution, the output is indeed 19,456. So the separable conv2D can indeed save a lot of parameters. After building several models, you may understand that there are a lot of parameters that we need to choose, such as the size of the layer, number of layers, the dropout probability. Those are called hyperparameters. Actually, there are several tools that can help us to optimize hyperparameters. Those are very important for our model accuracy. The package will use some algorithm like random search, genetic algorithm, Bayesian optimization to find the best parameter for our model. The original package is called HyperOpt, and actually the author combined Keras with hyperoptimization, HyperOpt. So it's called HyperOpt, Keras plus HyperOpt. So let's see what HyperOpt can do. It can vary the change the dropout probability or sampling by sampling from a uniform distribution, and it can try different output size for different layers, and try different optimization algorithms, or vary the choice of activation functions, or conditionally add layers depending on a choice. So you can add more layers for you or swapping some layers. So by using HyperOpt, you can fine-tune your model to get even better results. After you have fine-tuned your deep learning model as best as you can, the final trick to improve the accuracy is to add more different models. It's important to add models with different hypotheses. So you can try to combine deep learning models with SVM and KNN. This trick is called model ensembling. So by carefully combining the output of different models, you can almost always improve the final accuracy a little bit. There are some algorithms to do model ensembling. The most famous one is the random forest. It will give the different weight for different models. Other popular methods include the gradient boosted trees or in the wide and deep model. Here are the key takeaways of today's class. We can use the Keras API to go beyond the sequential model and build networks with branches. The Keras callback functions provide a simple way to monitor the model training. And you can control the fit function or the training functions by overriding the train step method in Keras model class. Beyond fit function, researchers can write their own training loops entirely from scratch by inherit the Keras model. They can try the brand new training algorithms. And finally, the separable convolution can reduce the model parameters significantly with same accuracy of the original convolution model.